Good morning or good afternoon, everyone. Thank you for joining our weekly Cognitive Systems Institute speaker series. This morning, we have Chieko Asakawa from IBM and Kris Kitani from Carnegie Mellon, who will present Cognitive Assistant for the Blind. Chieko is an IBM fellow known for her work at IBM Research in Tokyo, and she's been instrumental in furthering accessibility research and development for the past 3 decades. Her early digital Braille work in the 1980s is still helping the blind community in Japan to access digital Braille books. Her groundbreaking work in Voice Browser, the IBM homepage reader, which was made available in Japan, United States, Europe, and Asia, opened up the web and its information resources to the blind. She has many other inventions and accomplishments and is a recipient of numerous industry and government awards. Dr. Kris Kitani is a systems scientist of the Robotics Institute at Carnegie Mellon University, working in the area of computer vision. He has a bachelor's in electrical engineering from the University of Southern California and a master's and PhD in information science and technology from the University of Tokyo. During his time at Carnegie Mellon, he has worked primarily in the area of human activity forecasting, integrating optimal control and computer vision techniques to predict human activities before they happen. And he has won several Best Paper awards at prestigious conferences. So thank you for being our presenters this morning, Kris and Chieko, and I'll turn the call over to you.
Okay, so thank you, Diane, for your introduction, and good morning, everybody. So today we are going to talk about our research activities on cognitive assistance for the blind. In the first part, I will cover the background and an overview of the project, and Kris will focus on computer vision. Okay, first, let me start from the history of accessibility. Special needs influenced various innovations. Going back to the 1800s, many now standard features of telephones and keyboards were initially created to help people with disabilities. You probably know that captions for TV programs were invented for deaf people, but now are widely accepted for such uses as, sports sport and to help immigrants. You can easily imagine how OCR and voice recognition work was motivated by the needs of people with disabilities. Apple considered requirements from the blind community in the field. Google and other companies have been optimizing driving vehicles largely based on the hopes of the blind community, and the same technologies are going into mainstream. In this way, there is an ongoing trend from accessibility to general innovation. Okay, IBM has been a big part of this history. Back in 1914, IBM hired its first employee with a disability. That was remarkably early, long before our society began paying attention to such issues. In the 60s, IBM developed the talking typewriter shown in this slide. And talking 3270 terminal was developed in 1984. I was very lucky to use this terminal as the first group of users. You can see my picture in those days using the terminal. Various applications to help people with disabilities have been developed, especially in the last 3 decades.
I'd like to see if everybody can hear us. I think somebody else's mic is on.
Yeah, could everybody please turn their audio on mute? If you're on the phone, press the mute button, and if you are on the computer listening, press the little microphone button at the top of the screen to mute.
Okay, so the next slide summarizes the dramatic expansion of information resources for the blind, which I witnessed throughout my career, from paper to digital to the net. Before the 1980s, we only had paper-read and tape-recorded books as our information resources. Two significant innovations changed the situation. One was Braille digitalization, and the other breakthrough was voice-based web access. And my team developed the IBM Homepage Reader, the world's earliest voice browser. So the physical cyber world became accessible because technology changed our lives. But we still have challenges. For example, it is still difficult for me to work in unfamiliar locations. It is also difficult to enjoy shopping without a human assistant like my daughter. But anyway, my daughter is a much better shopper than I am, even if I could manage shopping by myself. So sometimes I feel like, the real test of cognitive computing will be creating a shopping assistant like my daughter. Okay, I will give you more examples. So finding good restaurants may be difficult for sighted people too, but it's much harder for us. Also, we are missing the signs, posters, and other visual information around us. I believe this poses a good technical challenges to computer scientists. Okay, let me share this old cartoon character with you. Actually, I was a fan of this cartoon when I was a child and could watch it. The little bird on his shoulder is a robot, and it helps the boy by whispering everything around him from the weather to approaching enemies. The bird had a telepathic link to the boy's mother, who came from a different universe. Okay, it's an animated cartoon, but I have often thought about this little robot since I became a blind researcher. One of my dreams is to create this kind of bird. If a small device on my shoulder could recognize everything around me, from parked bicycles, food in the meeting room, and color combinations of clothing, I believe this bird is a model for the blind, a tool to sense and make sense of the world. So, can we achieve such a bird with modern technologies? The answer is yes. Finally, the time has come. Most of you are familiar with this slide, but let me review. According to the advancement of data-oriented approaches, computers now can do many things based on massive data. For example, answering questions based on massive textual data, predicting the traffic jams for city planning, doing natural dialogues based on large voice corpora, and recognizing faces for a massive database. And also, these engines can be applied to substitute for the missing senses of persons with disabilities. That's why I'm so hopeful that things which are impossible today will soon become possible for the blind. Okay, now I would like to show you some videos.
Feet to the door. Take the two doors to go out the doors on your right. Nick is approaching. Looks so happy.
Oh, hi, Nick.
Hey, Chieko.
Where are you going? You look so happy.
Oh, well, my paper just got accepted.
Oh, that's great. Congratulations.
Thanks. Wait, how'd you know it was me and that I look happy? Hi.
Hi.
He is not talking to you, but on his phone. Potato chips. Dark chocolate with almonds. You gained 5 pounds since yesterday. Please take apple instead of chocolate. Approaching. You're right. Walmart is on your right. What do you want to buy?
I want to buy cookies.
Starting navigation to cookies. Please hold iPhone in front. Turn left 15 degrees. 2 steps forward. Bit forward. Go in front of the cookies. 6 kinds of cookies are there at left side. Second shelf from the top. Ritz Bit peanut butter. 140 calories. Oreo mini. 130 calories. There are many ways to eat Oreo. Do you want to check recipe?
Sure.
Please buy my book on the right side of the top shelf. Cognitive Cooking with Chef Watson. Recipes for Innovation from IBM and the Institute of Culinary Education.
Okay. I hope you.
That's fantastic.
Thank you. I hope you enjoyed the video. Of course, some of the technologies in video are still in the early stage, but important point is we are getting close to realize cognitive assessment. I classify necessary technologies into 4 layers. The first sequence of the video was navigation system. We need localization technology across indoor and outdoor environments to intelligently navigate people and deliver useful surrounding information. The second sequence showed the possibility of face and emotion recognition technologies, such as who he is, if he looks happy, or if he is talking to me. This information greatly helps blind people to be social. And object recognition is also very important. For example, in recognizing items in stores. It, of course, helps improve our shopping experiences, as you saw in the video. But it also helps our daily, lives by recognizing any item in our daily. The object recognition was backed by the knowledge base, ingredients, and
Excuse me.
nutrition.
Chieko, just a minute. There's some background noise. Kris, I'm going to try to mute all the lines, and can you just make sure your microphone on the computer is unmuted when I do that?
Sure.
So, Kris, I can hear you right now. Is it unmuted?
Can you hear me right now?
Yes. Okay, continue. I'm sorry for the interruption.
That's okay. So, ingredients and nutrition, my shopping history, my health status, and so on. And the user interface.
Chieko, can you speak up just a little bit?
Okay. So, do you want me to repeat from the somewhere? Okay. So, the object recognition was backed by knowledge database. Ingredients and nutrition, my shopping history, my health status, and so on. And the user interface was natural and contextual. Just a few words may change our lives. Nick, looks happy. These 3 words are really helpful for me to be social. We should advance these technologies. Okay, now let me turn to Kris.
All right, thanks, Chieko. So what I'd like to talk about is going to be specific to the second block here, recognition of the environment. So what I'll be talking about is how can we get the cognitive assistant to understand the functionality of an environment. So this is some new work that we're just about to publish. So let me set up the story a little bit. So when we walk into a room or a new environment, subconsciously, we know immediately how we can act in that environment. So I can show you this image of this living room and kitchen here. Without really thinking about it, you know that you can walk in these flat areas, even though you've never been to this room before. You know that you can also sit in these areas. So there's the ottoman and the sofa and there's the chairs around the dining table. We also know that we can open up these windows. We can open up microwaves, cabinets in the back. And again, this is just from a single image. So what we want to know from the perspective of computer vision is, can we teach a computer to understand this kind of scene functionality? And we like to do this by just observing people. That's generally the question that we want to answer. Here's the setup. We're going to give one or more than one person a wearable camera. So they're going to wear this. It could be on their chest or around their ear, just a small camera, or it could even be a smartphone. And what we're going to do is we'll record video from that wearable camera, and then we're going to detect actions using computer vision. Then what we're going to do is we're going to aggregate.
Too much background noise. Sorry again for interrupting, but we really need people to go on mute because there's just background noise.
Yeah, so if you can mute Mike, we would greatly appreciate it. Okay, so just to review the setup here, we have one wearable camera. We're going to be detecting human actions. So this is the human actions performed by the camera wearer. And then the third aspect is we're going to try to learn the function or the functionality of an environment just from that video data. So let me start off with an example. This is going to be a video of a functionality map that's learned for an environment, my student's apartment actually. And what we're going to see is a probability map over all the places that a person can open a door inside of a student's home. Let me play this. So let me first explain these three panes here. So up at the top, we have the action map projected to video. This is what the camera wearer sees. And projected onto there, we have these probability distributions over where the opening door activity can be performed. On the bottom left, we have the actual 3D point cloud that's being used to track and localize the camera wearer. And then we have an additional overview graphic here on the bottom right. And you'll see this purple box. This represents the camera. It's going to be moving around in the scene. So what I'd like you to look for are going to be red dots or red areas on the ground. That means high probability of opening a door. And then if you see something green, blue, purple, that means low probability of opening the door. So this person is just going to start walking around the environment, and you should see this open door probability being projected onto the video. So we see a peek there by the front door. We see a peek here by the closet. And we see another little peek on the ground for this door being out to the backyard. Right. So this is the idea. This is just one activity type. But the computer vision algorithm, by observing people, has learned that these areas are made for opening a door. So let me explain this pipeline. So the way the algorithm works is first, we'll require some type of walkthrough through the environment to build the 3D point cloud. This could be done by the camera wearer, or something could be done ahead of time. We have one or more scenes. We have two here illustrated. And once we've built this point cloud, what we're going to do is we'll have the person wearing a camera just walk through the scene and interact naturally with the scene. During this time, we'll have computer vision algorithms that are analyzing what the person is doing. And as we have examples here, we can detect things like a person walking down a hallway, writing on a whiteboard, washing dishes, opening a door. And these are all going to get recorded over time. In parallel to this, we're also going to be detecting objects in the scene using that same wearable camera. So things like the cups, sofas. We're also going to be doing a scene classification. So this is actually a pretty robust technology that exists today. You can take images of indoor, outdoor environments, and you can get a rough classification of whether it's, it's a kitchen, it's a living room, it's a cafe area. And so we're going to aggregate all of this information to build our model of functionality. So this information is going to get integrated into a matrix factorization algorithm. I won't go into the details here, but the idea is that if we can learn the correlation between activity detection and activity appearance in one scene, we could transfer that information to a new scene. So that's what we have here pictured with green. Right? We observe people in scene 1 sitting, and we could transfer that information to scene 2. So in scene 2, we haven't seen anybody really act in the scene yet, but we can make a good prediction of where a person might be able to sit in that second scene. Right. So as I mentioned earlier, one of the key components of this algorithm is the ability to be able to detect detect human activities using a wearable camera. Yep, so we've done a lot of work in this area, trying to build algorithms that are able to detect human activities using wearable cameras. And we really believe that this is key for building these types of computer vision algorithms that can support a cognitive assistant. And so this is just one topic. We're working in many other areas like predicting human activities, object recognition, grasp analysis, and we hope to really integrate a lot of this stuff into a cognitive assistant. Okay, so I'm going to be ending my part of the presentation and then asking Chieko to end with her final slide.
Okay, thank you, Kris. So it's going to be the last slide. So let me go back to this exponential growth slide. I discussed two innovations, digital braille and voice browsing, that enabled the exponential growth. Next is the real world. Cognitive assistance will enable blind people to recognize and manage the real world. And we will sustain the pace of exponential growth. And one day, we will achieve the level of sensory substitution, and we will realize the cognitive assistance. Thank you very much.
Chieko and Kris, this is fantastic. I had no idea we were this far along in doing the image recognition, and I love the phone app that Chieko used in the video. Let me ask our audience to please unmute your line if you have a question for Chieko or for Kris.
Hi, Chieko. This is Jim Sporer.
Oh, hi, Jim.
Hi. Great presentation. Thanks to you and Kris for presenting this on CSIG. I did have a quick question, well, maybe a comment. How do you see this getting out into commercial applications, or is it already commercially available in any platform?
Maybe let me answer first. So I think some of the technologies are available, like maybe you might know, like barcode reader. It is available for the blind people. So
right.
When we think about the commercial, things need to be really accurate, like and work in almost every domain. Only achieved, that point could be commercially available. But if we still limit the domain, I think there should be a lot of use cases. So like here in Carnegie Mellon University, we are looking for that aspect first, and once we ensure that, we can go for commercial or practical use, I think we can go step by step. So as you know, computer vision is really, what should I say? Long way to go.
Very good. Yeah. I will put in the meeting notice one of the companies that I know about that might be a good partner for commercialization of this. It's called World Around Me, and they have an augmented reality system for finding things in the environment, but I don't think they do any of the, they certainly don't do those really cool probability clouds for doors and stuff like that, but they do some other things that are kind of cool. So I put that in the meeting room notes, so you can check that out. I'll also post it to the LinkedIn profile later for this talk. Thank you, Chieko. Thanks, Kris.
Thank you, Jim.
Are there other questions? Robert, Bob Floss, do you want to ask a question? Come off mute.
While he's doing that, this is Frank. So I heard about all this from Carnegie Mellon originally. I was just wondering if Kris could spend a couple minutes saying what other research in this area is being done at CMU.
Okay, so with respect to the navigation for the blind, we have a couple of projects, and it's related to the NavCog app that was released at the end of last year. But we're still working on improving localization. We're working on new tracking algorithms that are kind of built specifically for this application, working in specific scenes. We're also working on a computer vision-based localization algorithm that will let the blind user walk through a new environment without it having to be instrumented. And then we would also be using that computer vision for identifying objects, of course. We have some newer projects trying to discover what people look at, what sighted people look at in scenes in general, and then see if we can sonify that, or if we can semantic labels for a blind person to give them more of a visual context of a scene.
This is Martin Appel. I have a question. I want to first compliment everybody on the incredible work that you're doing, but I'm thinking in terms of being the person that you're focusing on, and I'm looking at the question about how much can you do to ensure that they have both hands free as much as possible in order to be able to maneuver around their environment more easily. And the other question would be, if they're not on a level surface and there are steps, how does one take that into account and make it helpful?
All right. So the current app is a smartphone, so that does require the use of one hand. We are looking into a wearable type of harness that the phone can be put into. Also, the examples I gave you with the scene functionality understanding, that's done with a wearable camera. So it's a camera that's wrapped around somebody's ear, something like similar to a Bluetooth microphone. So I think a hardware interface like that, either wearable with a harness or around the ear, would definitely open up both hands. There are other kind of paradigms that we're thinking of, but those are the two I think that we're focusing on right now.
This is Bob Schlass from IBM Research in New York. Great work. What comes out to me from this is that the audio cues going to the user will take far fewer bits than had they had the visual cues. And that makes me think about the related problem of sending a robot that has video and perhaps radar and other things to a remote place, under the ocean, the surface of the moon, or just, a contaminated radioactive area or whatever. So could you say a little bit about whether your approach to video feature detection and probability clouds is similar or different than people who were trying to do kind of remote robotic control with limited bandwidth between the robot and the user controller?
I see. That's an interesting connection. Looking at it from the perspective of information, transmission. So the underlying technology, the building of the 3D point clouds, the localization of the self, that is common among many types of both robotic and its human-centric applications. What would probably make what we're working a little bit more specific to accessibility is that it's human-centric. So what that means is we're going to assume that the camera's on a person. Therefore, we'll use motion models that are going to be appropriate to humans, and also we'll be looking for things like hands and certain types of objects. So those kind of technologies need to be developed specifically for working with people. But as you pointed out, the underlying technology is the same. The math there, the geometry that's involved there is shared.
Thank you.
Yeah,
so we are out of time. This is Diane. I want to thank Kris and Chieko for an excellent presentation, and I want to thank the audience for your questions. We will see you next week, and thank you again to our presenters. Goodbye, everyone.
Thank you.
Thank you.
Bye.